Okay, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1206. Let's get the ball rolling here. Let's make sure I can see the chat and everything. All right, once again, let's start with a little quick review of what we did last time. Last time we covered the entire topic of optimization, a very, very important application of derivatives. And yeah, but in the Calc 1 sense, the problem types are going to all be similar, and the method by which you want to solve them will all be similar as well. So we went over that. So optimization is pretty much making something as good as it can be within some restriction. And oftentimes that can be rephrased in either making something as large as it can be to maximize something or find a maximum point of something, or to make something as small as it can be to minimize the size of something. So we had a 6-step process by which we went through to actually accomplish that based on some situation that was described to us. And we did 5 examples. The steps were to read the problem, to know that you're doing an optimization problem, which is pretty much going to tell you that by describing a restriction and a situation to you, and you're going to be asked to maximize or minimize something, or to find the best possible something. You're going to draw a diagram about that thing that hopefully will give you some ideas to set up these 2 equations, the constraint equation and the objective equation. The constraint equation is the equation that describes the restriction in terms of the variables that you set up in the diagram. And the objective equation describes the thing you want to maximize or minimize. You'll then find a new objective, which you use the constraint equation to plug into the objective equation to get it in one variable, because it will usually be in several variables, and we don't know how to deal with that in this context. You will then maximize or minimize the new objective depending on what you want to accomplish. And that will, since we're in calculus, we do that by finding the derivative, setting it equal to 0 undefined. And most of the time, not all the time, you'll get like one answer, and that's going to be your answer, because the problems I will ask you will have an answer. So it's not like you have to say, well, I have to check it to see if that's an answer, or maybe there's no answer. There will be an answer. So if you only have one thing, that's the answer. You can move on. You don't have to test it. I would only say to test something if you have several things, several answers that could give you a true answer. But only test them if it's not obvious. So you could have several answers, but maybe you have a negative. All the answers are negative except one. Then you can obviously ignore all the negatives if the thing you're talking about is a length or something, right? So after that, you have to answer the question. So a very specific thing is going to be required of you. Just make sure that you answer the question with that specific thing. So they might ask for dimensions, or they might ask for something else. Just make sure you end the problem by answering that question. So you'd have to interpret what the number you got in the previous step means to be able to synthesize an answer for the 6th step and final. So we did a bunch of examples like that. We did 5 of them. And then we went into talking about sigma notation and summation. So sigma notation is just a way that we can write down finding the sums of things in a concise manner. So that's the sigma notation, because that big E looking symbol is called sigma. It's a Greek letter sigma, uppercase. And it's a shorthand for just writing down a sum. So the AI represents each number in the sum. So a sub 1 is the first number, a sub 2 is the second number, a sub 3 is the third number, and so on. And so you can actually add them in this notation. And we looked at some formulas that we have in that notation. So these guys were very important, and you need to know them and remember them, as well as some properties in that notation. So these guys are also very important. You need to know and remember them. And we did some computation. So we computed the sum of 100 terms. We spoke about telescoping series, which is a very convenient kind of series, like a lot of terms cancel out, and so you really can add up the entire series by adding up only a few of them. We also spoke about partial sums, the sum of the first n terms, which we call S sub n. And we also saw that the S sub n's actually get closer and closer towards the entire answer. And this gave us a way to define the infinite sum. So an infinite sum, by definition, is just the limit as n approaches infinity of the sequence of partial sums. And that allows us to add up an infinite amount of numbers just by using limits. I also did an example of doing that, like we had to find this sum, where we're adding up an infinite number of terms that looks like this, right? So this would look like like 1 over n cubed plus 2 squared over n cubed plus 3 cubed, 3 squared over n cubed, etc. And that just, it kept going on forever, right? As your n approaches infinity. And it turns out that guy actually adds up to a third, believe it or not. So we looked at that and some, and that was it. That's all we got through. So we're going to need all that today. Yes, we're going to need all that today, and to start the second half of the course. And I also reminded you, as you can see here, an announcement for test 2. It will be starting on Saturday at 9 in the morning. It'll be open until Sunday, 9 at night, I think. So that's like a 36-hour window, which I think during that period of time, everyone should be able to do it. And I even spoke about the test covering everything that I'm going to get up to today, and everything else after that will be bonus material. Of course, we continue material next week. I think classes go up until Tuesday, and I also have an extra asynchronous lecture to post as well. So yeah, so that's that. Without further ado, let's move on. We are going to we're going to attack the error problem today, which I'm going to talk about a lot of ideas, so it's going to be nice to just like have that all typed out, I think. So we're going to attack this. I'm going to just have a discussion about where some of the things that I'm going to talk about come from. Where does the idea come from? And hopefully that can give you sort of an intuitive feel or some way kind of describe to you how did we end up here? Why are we even considering some of these things we're considering? Because if I just told you, it might be just like, wait, why are we doing this? So that's what we're going to be doing. So throwback to the beginning of class, I mentioned that there were two main problems that calculus was aimed at solving. And one was the rate problem, which the solution was the derivative, and we've spent a lot of time on that. And the other one was the area problem. So that's the problem that we're going to be focusing on now. So the area problem is pretty much the problem of figuring out how much space something takes up. In 2 dimensions, that's called area. In 3 and higher dimensions, that's called volume. And we just want to know how much space something takes up. And we spoke about why it's important to actually be able to know that. So geometry is probably the first area of math where you can remember this being even a thing that you would study. The thing with geometry, though, that you've seen before is that it was all about studying the area of regular shapes, where you can say, like, oh, that's a triangle, this is a rectangle, this is a rhombus or a trapezoid or whatever, oh, this is a circle. There's some very nice shapes that you know how to find the area of. However, there are some shapes that are very like random that you don't really have a formula for, but you want to be able to find the area of these things. So that's how we want to know what we want to deal with. So the thing is, how do you find the area of that, right? So what is the area of this? So we need to know what the area of some really weird shapes. And we also spoke about why we would even care. how would we go about accomplishing this? Well, the solution to the area problem has been known for a long time. There's evidence that even Archimedes, way back in like almost 300 BC, was already solving the area problem. And it came down to essentially cutting something up into smaller pieces for which you do know the area. So you can have this weird thing, like I said, that you'd want to be able to, actually, I don't think I need the lines, that you want to be able to find the area of, and you don't know because it's this weird shape. So what you can do is you can start slicing it up. So you can be like, okay, let's slice this up. And you can decide to, for example, dissect it into a bunch of rectangles, for which you do know how to find the areas of them, right? So you can actually find the area of these rectangles, 1, 2, 3, 4, 5, 6, 7, right? And you kind of add up the areas of the rectangles. And that will give you an approximation for the area of the thing. And wherever there is something that's not quite a rectangle, you can actually just guesstimate this. So you can guess what the area is based on proportions, like how much. It's roughly a little bit more than half of this rectangle, based on proportion. Or what you can do is cut it up further. So you can even go in and you can be like, all right, so let's even slice this up into smaller pieces, right? And we'll figure out the area of those, right? So the idea is essentially, is to cut up larger shapes. Oh, someone's hitting it. So the idea is to cut up larger shapes into smaller ones. And basically, you just say the area of the larger shape is going to be equal to, well, you're just going to define it to be the sum of the areas of the smaller shapes. And the smaller the shapes, the better the approximation. Okay, so that's basically the idea, right? But this isn't very efficient because essentially, if you do this and you think of this as your solution, then every time you encounter a new shape, you kind of have to go through all the motions of doing this again. You have to keep dissecting random shapes. Every time you find a new shape, you have to cut it up into a bunch of things. And every problem would be essentially new, and you won't have any sophisticated machinery. So this wasn't very useful. So thank goodness we now can, we have the XY plane, thanks to Descartes. We can talk about functions and things of that sort. So the idea is we can make this more sophisticated by using this other machinery that we have in mathematics. So we can take this guy and we can say, throw him on the XY plane. And then we can start to study it a little bit further, right? So now, essentially, the idea is going to be this, right? So we're going to take our shape, which is this guy that we care about, and we're going to dissect it, right? So we're going to like, all right, let's just figure out how to cut this guy up. And then you're going to realize, well, that's kind of going to be annoying if I'm putting it on the XY plane, because each vertical line is going to represent some X value. and each horizontal line is going to represent some y value. So now I kind of have to keep my eye on both the x and the y at the same time. So it's like I have two independent variables. That's kind of hard. So what we do is, to make it less complicated, you just dissect into one direction only, right? So you'll just say, all right, I'm going to dissect things vertically. So that way my x is tracking where the dissections are. I only have one independent variable here. And then you can create these shapes that you want. So you can do like, all right, I can dissect it into some rectangles. So the y only comes into play when you're finding the heights of these rectangles. But overall, you just have vertical strips. You don't have to worry about any horizontal strips, really. And so that can actually make the counting a little bit nicer. So now you try to, okay, let's generalize this. All right, so we go down, right? So we have this guy, and, all right, let's throw this on the XY plane. Go, all right, boom, 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 boom. So we have all these strips, and we want to be able to use what we want, the machinery that we have, to be able to talk about this. So I want to be able to describe this in terms of functions and the dissecting the function according to the x, according to some x values. The thing is, though, this guy, even if we dissected it, it's not a function, because if you were to hit it with a vertical line test, so it's not a function. Let's actually put that up here. So that's kind of a problem. So to combat that, what we do is, all right, let's just look at one half at a time, right? So we can just imagine the top half, right? So we can have this kind of thing going on. And now this is a function because it will pass the vertical line test. So yay, this is a function. So we can find one part at a time. So we can find the area of the top half by dissecting it into these little things. And then we can repeat the process for the bottom half, right? So this is the idea. We're kind of trying to figure out a sophisticated way to do this and to use the mathematical machinery that we have at our disposal. So that was kind of the first level of things. All right, we can dissect it in two sections, get a bunch of rectangles. Too complicated. Let's just dissect it in one direction, put it on the XY plane. Still too complicated because now it's not even a function anymore. It's going to make things harder, finding things like thinking of it as a function where I can use all my function machinery. It's not going to be good. So I can look at like one half at a time. All right, cool. So now we're down here. The strips are still weird because you'll notice that the tops are still irregular, right? So you'll see the top here. These are irregular. So what you can do now is you can actually make them a little bit nicer by just slicing off the tops, right? So boom, 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 right? So you have now a bunch of very nice shapes, right? They're all rectangles. We know how to find the area of each of these guys, right? So we can now create smaller shapes. Now, there's nothing that says you have to create rectangles, but that's the version that we're going to do first. So we can now create small rectangles. And we can use these guys to approximate it, right? So essentially, we now get these sets of rectangles that are approximating the area under a curve. And of course, the idea is if we need to get a better approximation, we can use more rectangles to kind of fill in these little spaces here. Like if I want to fill in that little space over there or any such space, I can just use another rectangle and get into the crevices even smaller, right? And so the idea is the more rectangles I use, the better the approximation, right? And on top of that, I can think of this curve can be thought of as a function. So you know y equals some f of x. And essentially now what you can realize is that the area of the rectangles will approximate the area under the curve. The sum of the areas of the rectangles. Will approximate the area under the curve, which will help us find the area of the original shape. So yeah, that's where we are. So this brings us into a more sophisticated method, because what you can realize now is that with this, essentially, I'll be able to figure out the height of any rectangle just by picking a certain coordinate. So if this is like some x here, then the height is going to be some f of x. And if I know like the x1, so f of x1, and I know like an x2, I can essentially know the height of the rectangle and the width of the rectangle. The width of the rectangle is going to be controlled by the x values that I sliced up the x-axis into. And the height of the rectangle is going to be given by this function. So I can know both the width and the height of a rectangle. I can use that to find the area. So a function can track the height of the rectangles for me. And so that's pretty nice. And so now we get into this idea of the area under a curve is what we need to figure out in order to find the area of some random shape in a sophisticated way. And we can use rectangles to accomplish this. Right, so you can have like boom, boom, right? So let's say on some interval AB is what we want to be able to figure out. So I can find that area, and I can get pretty good approximations depending on how I situate the rectangles. And on top of that, for the same curve, I can get better approximations by using more rectangles. Right? That would give me a better answer than this one. Right? And I can go even further. I can keep going like here's A, here's B, and make even smaller rectangles to fill in these spaces a little more. Right? And that's even better, right? So we can go from good approximation, better approximation, even better approximation. And the better we want to make our approximation, the more rectangles we use. And that's all there is. And so now, of course, we're the math people, right? So we want to get as good as approximation as we possibly can, maybe even theoretically getting to the actual area under the curve. And how would we actually accomplish that? Well, it's math, right? So we do have a concept that's not in reality, but it's in mathematics called the concept of infinity. So how would you actually get the exact area, right? If you care about the exact area, the idea is you'd want to fill in all the spaces. You don't want any of these spaces left over. So what you can do is you can use an infinite number of rectangles, right? So make the width of the rectangles very small, use an infinite number of them, and then it's like adding up the areas of all these rectangles, you would get essentially exactly the area under the curve. There's going to be no space left over because every time there's a space, you can throw in another rectangle. You have an infinite amount of rectangles to play with, right? So if in the case where you have, I didn't want to do that. In the case where you have an infinite number of rectangles, and get the area, right? Not just an approximation of the area, but the area, right? So that's sort of the idea, okay? And that kind of leads us into I don't remember what section this is, but maybe. So the thing is, I'm kind of jumping around explaining an idea that your book explains in like a few different sections. Like everything I'm explaining now is covered in like 1 or 2 sections in your textbook, but I want to kind of do them all together. So I'm actually also doing a little bit of 4.2 with you at the same time. So at least I think it's 4.2. And I'm actually going to go back to 4.1 a little later. Let me make sure. Let me check the syllabus. Make it a little bit easier to follow along. Although I think just following what I say can do it. Yeah. Okay. So that being said, let's actually now start to set up. Let's make this precise so we can actually know how to accomplish the kinds of things that I've been talking about. So let's come up with a process, like a strategic way to actually set up these rectangles to find their area. Like, how would you actually go about doing the computations? How would you go about actually applying these ideas that I'm talking about, like specifically, right? So we're going to go into, there are many methods to do it, by the way. And in Calc 2, you're going to see even more methods than we're going to discuss. So for now, we're going to discuss doing what I'm mentioning with rectangles. And we're going to see 3 varieties of how to do this with rectangles, but there are more. And it's also possible to do it with other shapes like trapezoids. And you'll see that in Calc 2. There's also a possibility to use parabolas or other polynomials to do this. You'll also see that in Calc 2, at least the parabolas version, which is called Simpson's rule. And there are many ways to do this. But in this class, I expect you to know 3 ways to do this. And I'm going to talk about those 3 ways. And I'm going to describe precisely what you need to do to accomplish that. So what this is called is something called the definite integral, right? And so the idea is, how can we make this precise? Well, suppose you want to approximate the area under some curve y equals f of x on an interval AB. You dissect the interval AB into smaller intervals, right? So that's going to be these guys right here. Right, like this and this and this and this and this. So you can create an interval. So this is an interval, this is an interval, this is an interval, this is an interval. These guys are called subintervals. Right? So it's when you take a larger interval, you break it up into smaller intervals. So this is called subintervals. So that's what I'm talking about here. Right? And what we're doing here is we want to do it into n subintervals, and we want them to be evenly spaced, right? And the length at which they're evenly spaced by is going to be called delta x, just a change in the x value between this. So this length here is going to be delta x. That's the distance, the length of each of these intervals on the x-axis. And so what you'll find is, if you have an interval AB, you want to cut it up into n equal sections. You can actually find the length of each section just by taking the length of the entire interval and dividing it by n, right? That will give you what each length is. What is the length of the entire interval? Well, it's right minus left. That's how you find a horizontal length. So you're going to take b minus a and you're going to divide it by n. So that leads us to the first formula that you're going to need to know. This thing called delta x that we care about is going to be b minus a over n. So that's going to be a very important formula. And that's always what we're going to use. So for Calc 1, we are always going to cut it up into a bunch n subintervals where they're all of equal length. And that length will be b minus a over n. Okay. So now that being said, how do you actually go about this? So suppose we can describe things as a function. There are going to be three ways in which we can do this: the left-hand rule, the right-hand rule, and the midpoint rule. And I'm going to describe each of them to you right now. So those are the three ways we're going to do it. They're all very similar. It's just a matter of how the rectangles get set up. So if you understand the first one, you'll kind of understand all of them automatically just by me telling you, oh, now position the rectangles this way. So let's talk about the left-hand rule. So here's what you're going to do. Here's a function. I want to find the area under this curve between a and b, right? So let's say a is here. And b is here. Okay. So the first thing you're going to do is you're going to do your dissections. Let's say, for argument's sake, I want to cut this up into 4 equal lengths, right? So I can cut this like here, cut this like here, cut this like here. So now there are 4 subintervals, right? Now the A is normally called x0, and the B is normally called xn, where here, that's x4, n equals 4 in this example. And then this would be x1, x2, x3, right? So I cut them up into like that. And the length of each is delta x, right? So the distance between x0 and x1 is delta x, distance between x1 and x2 is delta x, distance between x2 and x3 is delta x, etc., right? And so now I'm going to erect rectangles on these subintervals. These subintervals are going to form the base of the rectangles. And so when we're doing the left-hand rule, what this means is that the left side of the subinterval creates the height of the rectangle. So what does that mean? For each subinterval, I'm going to look at the left side, extend it until it hits the function, and then I'm going to cut the height off there. Move to the next interval, extend the left side, hit the function, cut the height off there. Next subinterval, extend the left side, hit the function, cut the height off there. Next guy, left side, extend, hit the function, cut the height off there. So left-hand rule, the left side of each subinterval determines the height. Okay. So now I can find the area of all these rectangles over here. And this is going to be an approximation for the area under this function between A and B. Now, of course, each of these guys will have a height. So this here will be f of x0 is going to be that, f of x1 is going to be that, f of x2 is going to be that, and f of x3 is going to be that. Notice that there's no f of x4 because f of x4 is on the right side. And so you only take the guys on the left side. So here, the area of the first rectangle is going to be delta x times f of x0. The area of the second rectangle is delta x times f of x1, etc. So I can actually now find the area here. Approximating the area into So here's what I can say by the left-hand rule. So it's going to look like A, the area is approximately equal to, you're going to have f of x0 times delta x. That's the area of the first rectangle. Delta x is the width, f of x0 is the height. Then you're going to add f of x1 times delta x. Then f of x2 times delta x. Then f of x3 times delta x. Or in other words, you can actually factor out a delta x, and you just have f of x0, f of x1, f of x2, and f of x3. Right? And so that is an approximation of the area. Now, using what we've learned yesterday, we can actually write this a little bit more efficient, because what this is, it's just adding up a bunch of things, right? It's adding up a bunch of things that have this form right here. So we can actually write this in summation notation using sigma notation. And it's like I'm adding things that look like f of xi times delta x. And my I in this case is going from 0 and it goes up to 3, right? So it's x0, x1, x2, x3. So it starts at 0, then counts up by whole numbers until it hits 3. So that gives you this idea here. So this would be called like, in this case, notice that this is n minus 1. So that kind of tells you the left approximation. So this gives you ln, the left-hand approximation for the area with n rectangles is given by I don't know what to say it's given by. I actually put this. So this is going to be equal to just a summation. I goes from 0 up to n minus 1 of f of xi times delta x. And that's just the left side, right? So that's how this guy is going to mean. We can actually develop a nice little formula for this idea, which is why we wanted to use functions in the first place. It takes this idea of, oh, just cut everything up into rectangles and just add them up into like, here's a formula for how to do this. Exactly. Like you do this, your delta x is going to be b minus a over n, and you're golden. This is the approximation. Now I can do the same thing, say with the right hand, right? So the right hand rule is when the right side of the subintervals determine the height. So I can do a similar trick. Here's my A, here's my B. I can dissect it into, say, 4 equal pieces. And then once again, this is x0, this is x1, x2, x3, this is x4 equals xn. And this time on the first subinterval, I go to the right side, hits the function, and then that's the height. Right side hits the function, that's the height. Right side hits the function, that's the height. Right side hits the function, that's the height. And then I can add up the areas of all these rectangles, and that's an approximation for the height. Okay. Now, here's what you would notice between these two, and it's going to be a similar idea. Here, here, you'll notice that your area is approximately equal to R sub n, which is going to be just the summation. I goes from 1 up to n of f of xi times delta x, because here you would have f of x1 is the first guy, then f of x2 is the second guy, then f of x3 is the third guy, then f of x4 is the last guy. So notice that this goes from 1 to 4, where the other one went from 0 to 3. So the first one starts from 0 and goes up to 1 less than n. The second one starts from 1 and goes up to n. Right? So that's why this is the formula here. And that will give you an approximation for the area. Another thing you can notice here is that, sorry, this is something on my screen. Another thing you can notice here is that, note for this function, this is not true in general, I'm just making a comment about the current example that you're looking at. For this function that I'm looking at right now, note that the left hand gave an underestimate. Okay. Why is that? Notice that the space that's missing means that the rectangles don't cover all the area under the curve. There's more area to be covered. So whatever the true area is actually going to be larger than whatever the left-hand approximation is with a finite number of rectangles. Here you can see that with this function, the right hand gives an overestimate. Right? And that can be clearly seen because the rectangles are actually above the curve, which means whatever the area is under the white line, it's actually going to be less than what's covered by these rectangles, right? So because of that, we invent a new method that kind of wants to minimize the difference between the underestimate and the overestimate in certain situations. If our function is increasing, then a left hand would always give an underestimate while a right hand will always give an overestimate, and vice versa for a decreasing function. The right hand will give an underestimate while the left hand gives us an overestimate. So we develop a new method that kind of tries to do the best of both worlds. And this is called the midpoint rule. Right? So here it's the middle of each interval. Okay, so so we can start the same way. Here's our A, here's our B. But instead of, and here's our x0, x1, x2, x3, x4 equals xn. Instead of using these x's, what we're going to do is we're going to use some different x's. We're actually going to take x's that are in the middle. So we're going to take this guy here. Let's call him x1 star. That's the typical notation. Guy in the middle here, x2 star. Guy in the middle here, x3 star. Guy in the middle here, x4 star. And these guys are going to be what determines the height. Now, if those guys determine the height, you're going to notice something that's going to happen. You're going to have something like this occurring. Notice that one side gives you an underestimate while the other side gives you an overestimate. So there's area missing from on this side, but then it overcompensates on this side. So we try to get a better answer more quickly by using midpoints to overestimate and underestimate at the same time. For this function. The idea is that you'll get to a more correct answer quicker by doing the overestimation and the underestimation at the same time. The idea being that they kind of cancel each other out and you get better, right? Which, yeah, normally you're doing this. And of course, this guy would be it's called m sub n, which is going to be equal to I goes from 1 up to n, but it's f of xi star times delta x. Right, so the length of the subintervals is still delta x, but here we have a height given by x1 star, x2 star, x3 star, x4 star. And that's the midpoint way of dealing with it. And the idea is you kind of get an area that's closer to the answer quicker, which on one hand, you might think, does this really matter? Like, chances are we're going to be using a computer to do this, right? Or if we're not using a computer, then we know we're not going to get to the answer anyway, because you can't ask us to do an infinite number of things yet. So is there a big deal in knowing that these different methods exist? And the answer is yes, because infinity can't actually be done. So if you wanted to program this in a computer, you want to ask your computer to create an integral. What your computer is going to do is it's going to use a finite number of rectangles regardless, because it can't have infinity. So it's going to keep going until the approximation is good enough to fill up whatever decimal place accuracy the computer can handle, and then it's just going to stop. And by that token, a computer having to calculate this for only 100,000 rectangles as opposed to needing 10 million rectangles, that's actually makes a big deal in terms of computing time, computing power. So you do want to know several ways to kind of set things up. And you can program your computer, well, if you have this kind of curve, use this method. If you have that kind of curve, use that method. And it can help you approximate them better. As well as you can have calculus methods, but we'll get to, I mean, technically we're already starting the calculus method, but there are sophisticated methods that we'll get to as well, if the function is very well known. So let's deal with that soon. But that's the idea, right? So this kind of tells you the way that you would set this up. So ultimately, it comes down to this, right? And these are methods that I do expect you to know. So I didn't just say all this for fun. Like these are things I'm going to actually expect you to be able to do and compute, which we're going to do some examples doing this. But I just want you to know where it comes from, right? So you can have a left-hand approximation, a right-hand approximation, or a midpoint approximation. In these, your delta x is b minus a over n. It's always going to be that. Your xi is going to be this. It's a plus I delta x. And I mean, and your midpoint can be done by finding the average between the two and then adding delta x after that. Now, why is the xi going to be that formula? I can show you. Why? Well, let's say you have this interval here. This is your x0. This is your x1, your x2, your x3, your x4, or xn, or whatever. And so remember, the distance here is delta x. Distance here is delta x. Distance here is delta x. Distance here is delta x, right? And this is your A, and this is your B. And so what you can do is, if you want to find this point here, right, your x1 is going to be A plus delta x. And your x2 is going to be your x1 plus delta x. But your x1 is A plus delta x. So this ends up being A plus 2 delta x. Then your x3 ends up being x2 plus delta x. But x2 is A plus 2 delta x, so this ends up being A plus 3 delta x. Your x4 would, of course, end up being x3 plus delta x, which is going to be A plus 4 delta x, and so on. That kind of just stands to the reason that your xn is always going to be A plus n, or let's call it xi. Your xi, your xi is going to be A plus I delta x, right? So that's where this formula comes from. And the midpoint, as you know, to find the middle between the two numbers, you just take the mean of those numbers. And so that's where that formula came from. Yeah. So this is going to be what we can do in the finite sense. And I'm actually going to ask you to do this by hand. It's usually going to be with like 3 or 4 rectangles, but knowing how to actually do this by hand is going to be important. It's also going to be important to know how to do it exactly. So, and we'll deal with that as well. So now to find the exact area under the curve, all you need to do is to use an infinite number of rectangles, where n actually counts the number of rectangles. So what you can do is just find the limit as n goes to infinity of this expression, and that can get you the rectangles. So this we know looks like the following. This is essentially, based on what we were doing yesterday, this is like you having an infinite number of infinity up here, right? But we saw yesterday what this really means is that you're taking the limit as n goes to infinity and the upper limit is n. So you can find the exact area by doing that. And we saw how to compute this yesterday. And so we use the following notation to describe this number. So here is the new notation. Okay. And this is called the definite integral of f of x on AB, right? So that's what it's called. So that's this new notation, which I should describe to you here. Let me write it a little bigger. So this thing is called an integral sign because the process of actually computing this area is called integration. We'll talk a little bit more about that. The A is the lower limit. This is the left side of your interval. The B is called the upper limit, the right side of your integral. The function is called the integrand. So just like you're doing the integral of something, it's called the integrand. Kind of in the same sense, like if I'm taking the radical of something or dividing something called the dividend, whatever, it's kind of that same nomenclature. The dx is the differential. We saw that guy before. It basically just tells you who the delta x is going to be. It's determined in terms of the x value. And this is called a definite integral. And it's finding the area under a curve f of a, b. And basically what this means, when you see this symbol, what you're actually calculating is this summation. Okay? So it's very important that you know that. So, and this equals this, right? Because when we're going to an infinite number of rectangles, it actually doesn't matter if you use left hand or right hand. So the standard way to do it is just think of it as the right hand, count from I equals 1, and it will fall in nicely with the formulas that we were discovering yesterday, because we also started at I equals 1. And that is actually the same as the limit as n approaches infinity. Where this guy, you can actually plug it in. This guy, is a plus I delta x. And the delta x is actually b minus a over n. Right, so that's what I put up here. You can actually put those guys in. Now, before we worry about that, which I will do, let's actually talk about the finite cases. Right, so here's an example. I will ask you a problem like this, just so you know. And it's going to look like this, right? Now, I am going to go through and I'm going to show you for left hand, right hand, and midpoints. But usually a problem in like an exam setting, I would only ask you to do like one of them, and then maybe find the exact answer. And so I'm going to show you how to do all of them so that no matter which one I ask you, you can do it. So I'm going to do all of them. I'm going to show you the process for actually calculating this and getting through the problem. But the problem itself, the statement is going to look very similar to this. Consider this function on this interval, approximate the area under the curve using 4 subintervals and left-hand endpoints. Or I can say approximate the area under the function using 4 subintervals and right-hand endpoints. Or approximate the function approximate the area under the curve on the interval AB using 4 subintervals and midpoints, right? So that's how the problem is going to be stated. Instead of in subintervals, I could say 4 rectangles, or I could say n equals 4, and it's expected that you would understand what I mean by that based on how we're setting up the theory. N always represents the number of rectangles, and it's also equivalent to the number of subintervals, because each subinterval is the base of a rectangle, right? So a problem can be stated like that. And now I'm going to show you how to actually do it. So our function here is x squared. Our function here is actually x squared plus 1, right? And I'm on the interval 1 to 5. Okay. So how are you actually going to do a problem like this, like the above? just take a step here and then get to it. Here's what you're going to do. The first thing you're going to do is you're going to figure out what your delta x is, because it's always going to be important, and it's actually relatively easy to figure out. So what you're going to notice is first, you're going to want to find your delta x. Now here, we have the interval is 1 to 5, right? So this is equal to your AB, right? So A is always the left guy and B is always the right guy, right? So this means that your delta x, I want to use a thinner one, it matches nicer with the type. Your delta x is going to be B minus A over N. That's always what it is. So you should just have that memorized. That's always what it's going to be. So it's going to be here 5 minus 1 over 4. Or it's going to be 1. That's it. Okay? So that's your delta x. Now, the second thing I would do is find the other xi. A nice way to do this is to sketch an interval and write them in using either xi equals a plus I delta x, or xi equals the previous x plus delta x, and picking the appropriate xi. So what would that look like? Well, I would actually just draw my interval here. I know that 1 is here, 5 is there. And I know that I'm dissecting this into 4. And I know that each length here is delta x long. So what I can do is from 1 to get to the next one, I'm going to add delta x. And then to get from this to the next one, I'm going to add delta x. To get from this to the next one, I'm going to add delta x. To get from this to the next one, I'm going to add delta x, right? You keep adding delta x, they're all the same size, right? So in this case, our delta x was 1. So I'm going to start at 1, then I'm going to add 1, right? And that's going to get me 2. 1 plus 1 is still 2 even in calculus. How do I get the next guy? Start at 2 and add delta x. Delta x is 1. 2 plus 1, 3. How do I get the next guy? Start at 3, add delta x. 3 plus 1, 4. So now you'd fill out all the guys on the subintervals. And now you just want to pick the right ones. How do you know how to pick the right ones? Well, look at the process you're doing. Here we want left hand, which means we're going to go, and on each subinterval, we're going to pick the guy on the left. So on the subinterval 1 to 2, I'm going to pick the 1. On the subinterval 2 to 3, I'm going to pick the 2. On the subinterval 3 to 4, I'm going to pick the 3. On the subinterval 4 to 5, I'm going to pick the 4. I pick the guys on the left because it's the left one, right? So those are the numbers I'm going to pick. Now, once you actually have that, you are going to set up the summation that we spoke before these guys. And so we'd really want to use the one for the left, right? Which you don't have to think in terms of these formulas anymore once you actually draw. Once you actually draw that picture, because the numbers that you're supposed to plug in will at this point be obvious. So, and by the way, I think did I mention this here? Yes, these guys are called Riemann sums. And in this case, we're dealing with the finite ones because the guy who discovered this method that I'm teaching you is a German mathematician by the name of Bernard Riemann. So these are called Riemann sums. So that's the third step. We're going to actually set up the Riemann sum. Okay. So what we're going to do here is we know that the area is going to be approximately equal to the L4. This is the left-hand approximation. AKA the left-hand approximation. Okay, so that's going to be the guy. L4 just means the left-hand approximation with 4 rectangles. And what is that going to be? Well, in this case, it's just going to be your delta x times, right? You know what numbers you want now. You want f of 1 plus f of 2 plus f of 3 plus f of 4. And now you're just going to plug these guys in. So your delta x, well, that's just 1 in this example. Your f of 1, well, your f was x squared plus 1. So your f of 1 is 1 squared plus 1. Your f of 2 is 2 squared plus 1. Your f of 3 is 3 squared plus 1. Your f of 4 is 4 squared plus 1. Right, so here, this is your f of 1. Here, this is your f of 2. Here, this is your f of 3. And here, this is your f of 4. And so here we have, well, and this here is your delta x. And so here you have 1 times 2 plus 5 plus 10 plus 17. Which is 34 square units. So this is the left-hand approximation. Any questions on that, on this process? So I explained to you the theory behind everything. When it comes down to a problem that you'll need to be able to solve, this is kind of what you'll be able to need to do. So I'll give you a function that I want you to find the area under on some interval. I'll tell you what method I want you to use and how many rectangles or subintervals I want you to use. So for example, if I say the left hand, first thing you're going to do is you're going to find delta x. You're then going to find the other xi by dissecting it, starting from the left endpoint and keep adding delta x until you get to the right endpoint. Then you're going to pick the right numbers that you want. With the left-hand rule, you pick the guys on the left. So you're going to start with x0, go all the way up to everyone except the last one. Leave off the last guy, but pick everyone else. Then you're just going to plug that into the formula because these are all a bunch of length times heights of the rectangles. And you add those up, and that's basically it. Now, with all the others, it's pretty much the same, except how you pick the numbers. What changes for the other ones is the numbers that are in the red circles. That's pretty much the only thing that changes, but everything else is pretty much the same. So I can start over with this problem and just pretend, oh, what if they ask me about the right hands as well in the first place? Then I can also do that. So what about the right hand endpoints? Once again, the first thing you're going to do is going to find your delta x. So you're going to have delta x equals b minus a over n. B is 5, a is 1, n is 4. Let's get 1. Second thing you're going to do, so used to choosing the second ones. Second one you're going to do is you're going to find the xi. So I would create that interval 1 to 5. I know I want to cut that into. Starting to. So I'm going to take this interval 1 to 5. I'm going to cut it into 4 equal sections. I'm going to start at the first one and add delta x. And keep going. 1 plus 1 is 2. 2 plus 1 is 3. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4. 4 plus 1 is 5. And I just keep doing that to get the others. And then now I pick the ones I want. Because I'm doing the right-hand endpoints, on each subinterval, I'm going to pick the right side. So everyone gets chosen except the guy far on the left, because everyone else is going to be the right side of some subinterval. And so now I can finally plug in and evaluate into my Riemann sum. Right? So here I'm going to have my area is approximately equal to the right-hand approximation with 4 subintervals, which is going to be my delta x times f of 2, f of 3, f of 4, f of 5. So my delta x was 1. My f of 2, 2 squared plus 1. My f of 3, 3 squared plus 1. My f of 4, 4 squared plus 1. My f of 5, 5 squared plus 1. So that is going to be 5 plus 10 plus 17 plus 26. 50, that's 34 plus 26. No, not 34. 34 was the answer to the last one. That's 15 plus 17, 22 plus 36, 26. That's 58. And that's the right-hand approximation. Notice that it's bigger than the left-hand approximation. So the left-hand estimate was 34 squared units. The right-hand was 58 squared units. And that's the entire problem. So you're going to have a problem. It's going to have a couple parts to it, and this would be one of them. So it's going to be like, all right, here's a function here on this interval. Approximate the area under this function using 4 rectangles and right-hand endpoints. And part A would be, approximate using right-hand endpoints, and this would be what you'd write down in this scenario. So unless there are any questions, I can move on. So this one, I want to use midpoints. So again, essentially it's the same process. One, I'm going to find delta x. Delta x is always b minus a over n. 5 minus 1 over 4. Two, going to find the xi. So I'm going to have 1 to 5. And to do this, right? So I know that I can add delta x. Add delta x, add delta x, add delta x, add delta x. So this is going to be 2, 3, 4. Now, remember we're doing midpoints here, so we want the middle value. So the first thing you're going to do is you're going to find the middle value. So we actually want the guys in here. Now, how do you get them? For the first one, what you would do is you would just find the average, 1 plus 2 over 2. That's 3 over 2, or 1.5, right? And you're going to put that here. So let me just write this in first. 3 over 2, that's going to be the first guy that you put in. Now, once you have the 3 over 2 or the 1.5, what you're now going to do is from that point, you can start adding your delta x to get to this one. And then you can, again, add your delta x to get to this one. Right, they're all going to have the same distance from each other as the original subintervals had from each other. So take 3 over 2, you add delta x, which is 2 over 2, you would get 5 over 2. Then you add 2 over 2, you get 7 over 2. Add 2 over 2, you get 9 over 2. Right? So that's like your 1.5, this is 2.5, this is 3.5, this is 4.5. And so those are the numbers that you would use here. which leads you to the third situation, which is going to be to set up and evaluate third step. Riemann sum. So in this case, your area is going to be approximately equal to the midpoint with 4. That's going to be your delta x times f of 3 over 2, 5 over 2. I'm already starting to square it in my head. 7 over 2, 9 over 2. It's going to be 1 times 3 over 2 squared plus 1, 5 over 2 squared plus 1, 7 over 2 squared plus 1, 9 over 2 squared plus 1. And I think I calculated this one earlier. This is, I think, 45. And I want you to notice that the answer to this is between the two answers here. But that kind of all makes sense, actually. If you look at this curve, the x squared plus 1, you would notice on the interval 1 to 5, it's actually increasing. So if I look at, say, so our function is like this. And it goes off like that. So this is your f of x equals x squared plus 1. Right? And we're looking at the interval from 1 to 5. And it's really wide. Let's make it a little bit. I don't know if that was much better. F of x Okay, so in one scenario, notice that the left hand would actually give you an underestimate. So if I look at like the left hand, make this here, left hand with these 4 guys. The left hand is going to give me this. Which is less than the actual answer, right? So that was the 34. Right, so that's that guy. We could also do the right hand. I think that was 58. So that would be like the blue coming up here and going over there. So that's clearly an overestimate. That's going to give you the 58. And then you had, I don't know what I'm going to use for this, pink. And then you had like the midpoint approximation, which was 45. It's actually going to be much closer. So this was like you have these points here in the middle. Right. So you notice that the green rectangle is going to be less than the pink rectangle, less than the blue rectangle. The blue actually gives you the biggest one because it's an overestimate. The green gives you a smaller one. It's definitely an underestimate. The midpoint, the pink one, gives you somewhere in the middle, though. However, we don't know exactly who is, what the exact area is here. But I can actually do a follow-up here. So maybe I can do that. So follow up to the above. Use an infinite Riemann sum to compute the exact area under the curve. And how would you actually go about doing that? Well, we know by definition that the area is going to be equal to that guy, which we know is equal to that guy. So if we want the exact area, this is the guy that we have to actually calculate if we want it from a Riemann sum, right? So, and the infinite Riemann sum just means we want the infinity up here. We want an infinite number of rectangles. Okay. So how would you go about this? Let's get through this one and then we can take a break. First thing you're going to do is you're going to, again, you want to find your delta x. And your delta x is going to be b minus a over n. This is 5 minus 1 over n. This is 4 over n, right? Here, notice n is going off to infinity, so we can't plug in a number for it. That's the first real difference. Then, again, you're going to want to find the xi. But we have a formula. Our xi is equal to a plus I delta x. So in this case, that is going to be our a is 1 plus I times delta x we found from the previous situation, previous step, 4 over n. So this is going to be 1 plus 4I over n. And then the third step, again, is going to be set up and evaluate the Riemann sum. So I know here my a is going to be equal to the limit as n approaches infinity of the summation. I goes from 1 up to n of f of xi times delta x. You can plug this in. This is going to be f of this expression, 1 plus 4I over n times our delta x, which is 4 over n. And we have that. So what we can do now is actually plug this in. This is going to be, our f of x is x squared. So it's 1 plus 4I over n squared plus 1. So essentially we want to compute this summation, which was actually very similar to the guy we did yesterday. That's what we're going to do. We are going to figure out this summation. So I would first start by expanding this. So this is going to be 16I squared over n squared plus 2 times this times that, 8I over n plus 1 squared plus 2. So what I can do here is, using the properties of the summation, I can actually just split these across 3 of them. This is going to be 4 over n times the summation of 16I squared over n squared plus 4 over n times the summation of 8I over n plus 4 over n times the summation of 2. Now, the 16 over n squared is constant as far as the summation is concerned. I can factor that out. And 16 times 4 is 64. Um, 8 times 8 times 4, 36. Plus, I don't have to factor anything out here. We have a formula for all of these. So the summation of I squared, we have formulas. For all of these. That we covered yesterday. So this is going to be n times n plus 1 times 2n plus 1 all over 6. This is going to be n times n plus 1 all over 2. This is just going to be 2n. So this is going to be 64 over n cubed times 2n cubed plus a bunch of stuff that I'm not going to care about, plus 36 over n squared times n squared plus stuff I don't care about, plus just 8. Now, as I take the limit, remember ratio of leading coefficients. This is going to be your 64 times 2 over 6, plus your 36 over 2, plus your 8. And two into 36, that leaves you with, I want to say, 18. 2 into 6 goes 3 times. 3 does not evenly go into 64, so this is 64 over 3. The 64 over 3 plus 26. Uh, 26 times 3 is going to be 78. 64 plus 78. Like 1, 142, which that's roughly 47.3. So that's going to be the actual answer, right? So it turns out the midpoint approximation was the closest with 45. The actual answer is actually very close to that. That would be the infinite Riemann sum. So a lot of algebra, as you can see, which is going to be why in the second part of the class, I'm going to want to develop, well, I'm sure we all want to develop a much nicer way of doing things than going through that whole mess. There's got to be a better way, like, right? So this is equivalent to finding derivatives by definition when you have to do that limit as h approaches 0 of f of x plus h minus f of x all over h. And it's like, you do that for a few functions and you're like, that's kind of annoying. I don't want to do that anymore. So we developed these shortcut rules, the power rule, quotient rule, chain rule, product rule, all that good stuff. So we can do this a lot easier. In the same way, to actually find the exact area by hand, it can get pretty messy, even with a very simple function. Like y equals x squared plus 1 is not a complicated function. But yeah, we need to go through all this mess to find the area. So in the next section, we're going to start to develop a way to get to the answer for a problem like this a lot quicker. And that's kind of going to lead us into a very important theorem that we want to deal with. But for now, we will actually take a break. I know we covered a lot here. And most of it was just like theory, though, like me telling you why we would even approach it this way. But what you need to be able to do are these examples, right? So I give you a function on an interval and I ask you to approximate with a finite number of rectangles. It's going to be 3 or 4. And then I would ask you a follow-up to say, hey, find the exact area using a Riemann sum. in which case you'd have to do this and get to that answer. And then there would be a third part to actually find the answer without doing any of this, which is a lot shorter. And so you can appreciate all the different methods, the evolution of this idea as we go fully through it. But to show you the shortest method possible, I have to give you some more theory and teach you some more stuff behind it, which is what we will do in a little bit. So for now, we're going to take a break, give you guys about 10 minutes, and yeah, we'll come back and start to make things even more streamlined than they already are. So yeah, we'll return in 10 minutes and we can do that.
The show will start in 9 minutes. The show will start in 8 minutes. The show will start in 7 minutes. The show will start in 6 minutes. will start in 5 minutes. The show will start in 4 minutes. The show will start in 3 minutes. The show will start in 2 minutes. The show will start in 1 minute. And now, on with the show.
All right, let's continue. Before we continue, I in fact made a little typo in the last time. I think I had a 36 here. Should have been 32. So the answer changed slightly to 136 over 3, which is, it's actually even better. It's actually 45 and a third. So turns out with just 4 rectangles, the midpoint rule got it pretty close, got 45 as the approximation. And that's what I meant with the efficiency of which method you choose can actually vary greatly, right? So the difference that we get between an infinite number of rectangles and only like 4 is like a third, right? All that extra work for like 0.33, right? So sometimes it's nice to know several ways to configure the problem because you can actually get pretty close depending on what situation you're looking at. So yeah, that being said, this is a problem type that you would need to know how to do. Approximating area via Riemann sums in the finite case, in which case I'm going to ask you like 3 or 4, and as well as approximating not approximating, actually finding it with Riemann sums, the exact area, which means you have to do the infinite case, in which case you have to, based on all the stuff I did yesterday, you would be able to do that. Although the arithmetic might be very annoying. Although in class, in a test, I wouldn't give you something this annoying. This is actually way more annoying than I would actually put on a test. Because this would be like one part of like a 3-part problem. I'm not going to go too crazy here. So yeah, we will wrap that up there. And this is all it's somewhat preliminary, but these calculations that I just did are actually in, I want to say 4.2. Yeah, I think it's in 4.2. But it just flowed nicer to do it ahead of the other stuff. We're actually going to jump back to 3.9, which is where the formulaic setup for the thing that I will be teaching you is done in 3.9. So I'm actually going to go back there. I'm going to talk about something called antiderivatives, and then we will continue. And that's going to help us actually do these calculations a lot easier. So next section, no, I don't want to insert space. Okay. So now what we're going to do is we're going to move on to the next, to start actually going back into our syllabus and try to follow the text for a little bit. We're going to do 3.9, which is antiderivatives. Hyphen is not always used, but sometimes. Okay, so we're going to talk about the notion of an antiderivative, right? So we know what a derivative is, and what would an antiderivative be? Well, it's kind of like what you think it is, right? It's kind of the anti goes the opposite way. It's essentially we want to be able to reverse a derivative. So let's actually talk about that. So definition, let f of x be a function. An antiderivative of f of x is another function could technically be the same function, it's like 0 or something, is a function big F of x, which is like very commonly used, such that if I take the derivative of the big F, I would get the little f, right? So the antiderivative of a function is some other function that if I were to differentiate it, I would get the function that I'm currently looking at, right? So that's called the antiderivative. So actually computing an antiderivative is therefore equivalent to reversing the derivative, because I wanted to find what function did I differentiate in order to get this function that I have right now. That function is called the antiderivative, right? So example, an antiderivative of, say, of f of x equals x squared is, here's one, you can have 1/3 x cubed. Okay, so that's an example of an antiderivative. How do I know? Why? Because if I take f prime, I would get 1/3 times 3x squared. The 3's would cancel, and I would just get x squared, which is the original function. So that is equal to the original f of x. Okay. So 1/3 x squared is a function that if I were to differentiate it, I would get x squared. Therefore, I can say an antiderivative of x squared is 1/3 x cubed. Hopefully I said that before. Here's something I want you to note. Antiderivatives are not unique. That's why we defined an antiderivative in the definition. Right? If you look back at the definition, I used an antiderivative. It's because there can be many. In fact, there always is. There always is many. You can actually always have an infinite amount, right? So, example, f of x equals 1/3 x cubed plus 7 is also an antiderivative. Of f of x equals x squared. And again, that can be seen easily, since if I were to take f prime of x in this case, that's like d dx of 1/3 x cubed plus 7. That's going to be 1/3 times 3x squared plus 0, which is x squared. I can get x squared again. And of course, so is, say, big f of x equals 1/3 x cubed plus 9, or big f of x equals 1/3 x cubed plus pi, or you kind of get the idea. We can, in fact, keep going. So I can say, or in general, big f of x equals 1/3 x cubed plus c, where c is an arbitrary constant. is an antiderivative of x squared. So even a function as simple as x squared, y equals x squared, or f of x equals x squared, has many antiderivatives. It has an infinite number of antiderivatives. Every time I add a constant to 1/3 x cubed, I get another antiderivative of x squared, right? So it's just some function that I had to differentiate in order to get x squared, which means if there was a constant term, the derivative would just turn it into 0 and it would disappear and I would have that, right? So this leads to another definition about a general antiderivative. So this kind of generalized thing, with a plus c. So suppose big f of x is an antiderivative of little f of x, and big f of x has no constant term. Right? Then this is then this expression big f of x plus c is called the general antiderivative of f of x. And that just generalizes the idea, because every time you add a plus c, you can get a new antiderivative. So some remarks. In the above context, big f of x is called the primitive and c is called the arbitrary constant of integration. Right, so people will say it's just an arbitrary constant, but they really mean an arbitrary constant of integration. They usually don't say integration. What else? Even such an f of x may not be unique. And I think we'll see some cases like that. Whereas it's like with trig functions, you'll have guys like that can be antiderivatives, but some trig functions are just shifts of other trig functions. Like you can think of like a sine function as like a shifting in a cosine or something like that. And so sometimes you can do sort of this like this vertical shift or this horizontal shift and create a whole new function that is somewhat equivalent to the previous one, but it's actually different. And you could create something like this with it. But this, we tend to call it the general antiderivative. That's because of the plus c it makes it a lot more general. So we can say that the general antiderivative of f of x equals x squared is x cubed over 3 plus c. And so we could say that phrase. Now, we do have shorthand for this. And here's a notation: the general antiderivative of f of x is denoted by this symbol, which is, again, the same guy that we had up here, the integral sign. We had him up here somewhere. That guy, except the difference is going to be that we don't write numbers on it. So we just have this with no numbers written on it, right? And it is called the indefinite integral. F of x with respect to x. Okay. As opposed to the guy that was up here that we called the definite integral. You can see it here. So you have a definite integral. That's when you put numbers on it. That guy represents the area under a curve on the interval AB. Without numbers on it, like this, you just write it without numbers. It's called the indefinite integral of f of x on AB, right? So that is a difference. Now, you might be thinking, well, I mean, did they kind of like run out of notation here? Like, why do we denote these things so similar with the only difference is numbers are written on the symbol? And of course, there is a reason why it's written so similar. It turns out that antiderivatives do have a connection to area, which we're going to talk about pretty soon. So we can write this guy equals big F of x plus c. And that makes sense to write down. Example, I can write this expression. And that would make sense to write. And how we actually talk about this is we can call this, we can say the general antiderivative of x squared is is x cubed over 3 plus c. Or I can say it another way. I can say the integral of x squared is x cubed over 3 plus c. Right? And usually when we say integral, we mean indefinite integral. FYI. When we say integral, we usually mean the indefinite integral. Usually when definite integral is implied, is intended. We'll say exactly that. So you have two kinds of integrals that I described in this lecture. There's the definite integral and there's the indefinite integral. Usually when someone says integral, oh, the integral of this is blah, the integral of this is blah, they're talking about the indefinite integral. If anyone means to say the definite integral, they would usually emphasize the word definite. They would say the definite integral. They wouldn't say, oh, the integral. But again, that's usually, you could have someone who means one or the other, and it's just about, it should be clear from context what the person is talking about. But yeah, so that is the notation for antiderivative, and that is what an antiderivative is. It's just some other function that you differentiate to get this function. So the antiderivative of this function is another function that I had to differentiate to get this function. So it's like, if I'm searching for the antiderivative of this guy, it's almost like I'm trying to reverse the process of derivative to find out who was the original function that I differentiated to get this guy, right? So that's the idea. And there's the idea of a general antiderivative, which is denoted by big F of x plus c, and we can denote it in symbols using what's called an indefinite integral. And we can write down an expression like this, and it would always make sense in that situation, provided the big F actually matches with the little f. And so I can write, for example, that the integral of x squared dx is equal to x cubed over 3 plus c. I want to put some more remarks on the notation. Now, there's going to come a point where this is actually super duper important. That point is usually around Calc 3. However, you are going to want to build good habits starting now, just in case any of you are going to end up in Calc 3, you don't end up messing up because of this silly habit. As I mentioned, notation is actually super duper important. Like, a lot of the times, doing well on a test or being good at math is a matter of how good are you with the notation. If you're sloppy with math notation, chances are you're not going to do well. It's that big of a deal. Even though students rarely think it's a big deal, they just kind of sloppy with how they write things down. Notation is a big deal. It can make a night and day difference, to be honest. So I do want to talk a little bit about notation and some things that you want to pay attention to when you're writing down the notation. So in, say, the integral of f of x dx, did I think I'm pressing something on my own screen? The dx part is important. Always write it. Same is true for, if you have a definite integral, you have a little a to b of f of x dx. Okay, so it's important. You should write it down. So that's the first thing. Students often just don't write the dx. They would write, oh, x squared and then equal blah, blah, blah. Doesn't make any sense if there's no dx there. That's the first thing. So writing, maybe I should leave that up. Integral of x squared is incorrect. You must write integral of x squared dx, right? So don't leave off the dx. That's the first thing. Second thing is how the dx functions. Not functions. How the dx should be written is always going to be what you want. So the dx is always after the integral sign and to the top or right. And to the top right of the integrand, right? Always. Okay, so what do I mean by that? So these are okay versus, what are you doing, man? So I can write, say, the integral of, say, 1 over x squared dx, or I can write the integral of dx over x squared, or I can write the integral of 5 dx over x squared, or I can write 5 over x squared and put the dx off to the side, or any such version. But then if I do something like write dx and then write 1 over x squared, like what are you talking about? The dx should be to the right or above, top right all the time. That doesn't make sense. Or if you have 1 over x squared and the dx is in the bottom, what are you doing? You can't have that, right? Or it's like dx 5 over x squared. No, not a thing. Or dx times x squared, like that. Like, no, not a thing. The dx is always to the top and to the right. And this actually helps you out computationally later on down the road. But just make sure you get into the habit of always writing the dx to the top and to the right. Top right, all the time, always. Dx is to the top and to the right. It's never going to be in the denominator, because if it is in the denominator, that's an indication that it needs to move. So when you get to a class like differential equations, there will be time where your dx's or your dy's and whatever, they're all over the place. And the first order of business in a problem like that usually will be to position everything so that the dx's and the dy's are to the top and to the right of whatever equation they appear in. And that's going to help you figure out what you need to do next, right? So the position of the dx is super important. So yeah, top right all the time, every time. So That's something with notation. Write the dx, write it in the correct position all the time. You stand to get yourself in a whole lot more trouble if you're not doing that in future math classes. And in this math class, like if you misuse the notation, I am going to deduct points for it. So yeah, just write down the correct notation. Okay. What else do I want to say? I probably want to talk about, at this point, some general formulas would be nice. Is there anything I want to say before that? Well, I planned on telling you something before that, but I think at this point I can actually just say this right now. So, more important remarks. Finding an antiderivative is essentially trying to reverse a derivative, right? So for example, I recognize that if I were to take d dx of 1/3 x cubed, that would leave me to x squared, which is the derivative. Finding the antiderivative is going from x squared to there, right? This is the antiderivative. Right, so this would be the antiderivative. The x squared would give me back the 1/3 x cubed plus c, right? So the derivative does something. The antiderivative tries to say, well, what did this come from? And so that actually gives you a very nice rule or an idea that can be very, very useful when it comes to computing antiderivatives. And it is going to be very important and useful to compute antiderivatives, which I'll talk about pretty soon. So this means every derivative rule can be repurposed as an antiderivative rule. So for example, if I told you the derivative of sine of x is cosine, it means the antiderivative of cosine is sine, right? I can just kind of turn it around the other way, right? Because the derivative would do something, and then the antiderivative is just trying to bring it back, right? It's not quite, but almost like you're taking an inverse function. If you think of the derivative as applying a function or a rule to some formula, the antiderivative is trying to perform the inverse function. It's trying to figure out where did that thing come from. And that's not exactly 100% accurate, but that's like 99% of the picture, right? There's a little 1% difference that we will make precise next class. So yeah, you can know that is true. So So from this, we can readily develop antiderivative rules. So an important one. The power rule for integrals. Right, so this is what comes from reversing the power rule. So when we say the power rule, we're normally talking about derivatives, but there is an equivalent power rule for integrals where you're kind of trying to reverse the power rule. So it's when you have something like x to the n and you want to find the antiderivative of that instead of the derivative. So we know for the derivative, so this is essentially the reverse of the power rule for derivatives. Okay. So remember how derivatives work. Okay, so you have some function and it has its own power, but you're going to change the power. So the power it currently has is going to be the old power that it has. So you're going to multiply by the old power and then subtract one from the old power to get the new power. To reverse this process, what you're going to do is instead of multiplying by the old power, you're going to divide by the new power. And then instead of subtracting one from the power, you're going to add one to the power. You're just going to do the opposite. Then at the end, you're going to put that plus c attached to it because if there was a constant being added, the derivative would have gotten rid of it. So this becomes the following. Instead of subtracting one from the power, you're going to add one to the power. And instead of multiplying by the old power, you're going to divide by the new power, right? And then you're going to add plus c. So this is a very important rule. And in fact, you can see as an example, this was what we did with the antiderivative of x squared. We added 1 to the power, and then we divided by the new power, plus c. That gave you that x cubed over 3. Which you could check for yourself was actually the derivative. But you can now do this in general. So I can say antiderivative of x to the 7th. Well, that's x to the 8 over 8 plus c. Antiderivative of x to the pi. Well, that's x to the pi plus 1 over pi plus 1 plus c. Now, obviously here, there will be an issue if your n is minus 1. So notice here your n cannot be minus 1 because then you'd end up dividing by 0, right? So now, if n equals minus 1, the power rule does not apply. But we do know how to deal with that anyway. Again, by reversing a derivative rule. So, of course, you know that if I have x to the minus 1 power, this is just the same as 1 over x. So this means the antiderivative of x to the minus 1 power, it's the same as saying the antiderivative of 1 over x. So now you just have to think, well, what did I have to differentiate in order to get 1 over x? And obviously that comes from a logarithm, the natural log. But we can generalize it. So this leads to since we know that the derivative of ln of absolute value of x is equal to 1 over x, This accounts for both positive and negative values of x. That's what the absolute values do. Accounts for x greater than 0 and x less than 0. So this means that the antiderivative of 1 over x dx is going to be ln of the absolute value of x plus c. So that's another rule. So this is if we have n equals -1 in power rule, we get the natural log instead. And the absolute values are important. Okay, so if you say the antiderivative of 1 over x dx is ln x plus c, this is wrong, right? The antiderivative of 1 over x dx is ln of absolute value of x plus c, right? Okay, so the absolute values, they are important. Don't neglect them. So that gives you 2 rules that you can apply in general. By using the reverse a derivative rule idea, we can develop many antiderivative formulas for almost free. So some are, well, of course, there's the power rule. We have this one for 1 over x. We have, for example, for e to the x, right? Since the derivative of e to the x is e to the x, we can have for the sine of x, that's the negative cosine. For the cosine of x, that's the positive sine plus c. We can anti-differentiate secant squared. We know that gives us tangent because the derivative of tangent was secant squared, and et cetera, et cetera, et cetera. Like we can have a bunch of rules for free because we know the derivative direction. We can automatically know the antiderivative direction. So that's pretty nice. And antiderivatives have very similar properties computationally as derivatives do, because you're pretty much reversing them. So also antiderivatives have similar algebraic properties. To derivatives. I.e., there is a constant factor rule which means you can factor constants in and out of antiderivatives. So if you have the antiderivative of some constant times a function, you can move the constant out and just find the antiderivative of the function. So just like with derivatives, you can just kind of ignore any constant factors, just leave them alone, do your magic on the variable part, and then just multiply the thing. So example, if I had the antiderivative of 7x cubed dx, this is just going to be 7 times x to the 4th over 4 plus c. So it's 7 over 4 x to the 4th plus c, right? And that would be the answer, right? You just leave the constant alone. You can just do the antiderivative on the function part, on the variable part. So constants can factor out. There is also a sum difference rule. So that is to say that the antiderivative of a sum of functions is actually the antiderivative of the individuals summed together. The integral of a sum is a sum of integrals, right? Example, the antiderivative of, say, x to the 4th plus e to the x dx, that is the same as applying the power rule to the first guy and applying to the exponential rule to the second guy and plus c. So that would be the same as doing the x to the 4th first and then doing the e to the x second, but you don't have to write this line. You can just jump ahead. Okay, so you have your x to the 5th over 5 plus your e to the x. So that's nice. And also, as with derivatives, you can mix and match these properties. So you can have say I have the antiderivative of, say, 5x 10x to the 4th minus 3 over x plus 2. I can think of this as, well, it's 10 times x to the 4th dx minus 3 times 1 over x dx plus 2 dx. I don't have to write this line. And so that would be like 10 times x to the 5th over 5 minus 3 ln of absolute value of x plus 2x, right? Derivative of 2x is 2, so the antiderivative of 2 would be 2x plus c. We can simplify this. 5 into 10 goes 2 times. So that would give you 2x to the 5th minus 3 ln of absolute value of x plus 2x plus c, and that would be the answer. So you can factor constants out while you're splitting things up, and that's okay. So computationally speaking, we can do that. And another example while I'm here is sometimes you can apply the rules even when it's not immediately obvious, just like with derivatives. Remember, you always try to apply the most basic rule possible first before getting too complicated. That was a lesson that not all of us learned by test 1. Hopefully we get to that by test 2. So there are times when you can have something that looks very complicated, and I can ask you, find the antiderivative of this thing, and it looks complicated, but it's not really complicated, because if you just applied algebra to it before doing anything, it would actually be not bad at all. So what am I talking about? Something like the following. Let's say I had 5x squared plus 2x minus 7 all over x squared. Right? Not the most complicated looking thing in the world, but it's more complicated than anything we've seen prior to this. So you have that thing. What you could do is you could actually simplify it first. So let me write out a line that you wouldn't necessarily have to write, but just so it's clear what I'm doing. It's legal to just actually divide this into each part. Don't have to write this line. So you would be able to simplify this. This is just the antiderivative of 5 plus 2 over x minus 7x to the minus 2 dx. And so antiderivative of 5 is 5x. 2 over x is 2 ln of absolute value of x. And for this guy, I'm going to add 1 to the power, which gives me a minus 1, divide by the new power. Maybe I should actually write that out. Plus c. And that would leave me with 5x plus 2 ln absolute value of x plus 7x to the minus 1 plus c. Or do 5x is 2 ln absolute value of x plus 7 over x plus c. So sometimes you can have situations like that where it looks kind of scary and convoluted, but you can actually simplify and get a bunch of separate and easier things to deal with just by applying algebra before you try to apply the calculus part. I think I have to stop there because, yeah, there's another topic I want to get into, but it's not something I'd be able to do in a few minutes. But it's a very important topic. So the next class is going to be super important. And that's what's called we're going to talk about the fundamental theorem of calculus. Yeah, so I think we can stop there for now. We did less than the 3 hours, but it doesn't make sense, I don't think, to start now. It's going to go over too much. So we'll stop there. So again, you'll have the notes. So for the test coming up, I expect you to know everything up to being able to take basic antiderivatives, as well as, so all the derivative stuff that we've done since test 1. Like the related rates, optimization, linear approximation, all that stuff, all the way up to going through Riemann sums, finite and infinite, and computing basic antiderivatives. That's what the test is going to cover. Everything else would be do we do anything else? So test 2 is going to cover everything we did since test 1. I forgot exactly at what lecture we stopped, but it'll stop here. And then the bonus material will cover from 4.3 onwards. So the only topics we have left. So I think I went through 4.1 and 2. And so the only topics we have left, I think, is 4.3, 4.4, and 4.5. Yeah. So 4.3, I think 4.3 and 4.4, I can take care of. I want to do both of those kind of in one. So that'll be next class, Monday. And 4.5 would be Tuesday. And I might even have time for some other stuff. And I still have an extra lecture, which I will maybe just keep going and expand on things some more. So that's kind of the current plan. Yeah, so we have 3 sections left to cover, and that's what the bonus is going to be on, and that's what we'll be doing next week. So Monday, Tuesday, and the asynchronous lecture. So for now, that's it. This is what you need to study up to at least for Saturday. And yeah. So good luck with that. For now, I will let you guys go. It's already late. Everyone's frazzled. So I will see you guys on the next one.